Welcome to Statistical Mechanics, Part 6. Let's go. Little late today, so we gotta grind even harder to make up the time. Welcome back, Galva. Just testing if Mrs. S's sum makes sense, and improving a bit on her notation. It really should be. I think it's easier when you say that the partition function in the exponential, that the sum goes from I to n, and really that it's ei of ni. So the ni was just ground state or excited state. Oh yeah. Oh yeah, the squiggly. You could think of the notation under the sum. Basically, it's more clear if they had written this. Because the squiggly, when you have the squiggly under the sum, it means that you are supposed to test. You're supposed to put that n1 is 0 in here, and you're also supposed to make another term twice the sum when n1 is 1. That's why you get these 4 possibilities, because I have 2 particles and it's a 2-level system. So now here it takes, because of the squiggly sum, it takes ni 0, I mean n1 0 and n2 0, and it takes and it makes a new term with n1 0, n2 1, and then a new term with n1 e epsilon. No, sorry, n1 1, and then n2 0. So here it is n1 1 and n2 1. Yes, I can. Still the same as yesterday. Just have to make sure that I understand Mrs. S notation. You should try to make the connection to the way you explained it yesterday on the interactive board thing, because you got the same answer and it seemed like a good explanation. This is just and it was more intuitive, but Mrs. S is heavy on math. So now that I think I understand it after your explanation, I'm like going through what she did and her notation. And actually improving her notation a bit, making it a bit clearer. Because she just said the sum of I, and then you have no idea what I really is, unless you know what I is. And we finally understood yesterday that I is supposed to be the system number or system index. Yep. Hmm. So you maybe think that Ni is like in the Harvard, that Ni is number of particles in a given state. I watched a bit of lecture earlier, and my professor also uses the blue wizard. He also uses Ni as number of number of particles in a given state. I can try and see. Maybe I have like a wrong notation, but it still works. That's possible. Maybe I'm calling Ni what is actually supposed to be I. Yeah, I also seen that what you lastly said now, and that's the common notation, so maybe I should try to use it as well. You mean differentiating when we're finding the average? Oh yeah. So then that would mean that I is 0 or 1, right? Okay, then let's see if Mrs. S's notation makes any sense. Or if she's using the same. what I think it's weird is how can you have E of Ni? Bro, using shredding. Mr. 𝐒𝐚𝐲𝐿, we are working with the partition function. And we're working at task 2-1. So what I'm wondering about now is maybe first then we need a new explanation of what this means, because is Ni basically a tuple or in the programming language? But yeah. Because normally when you had the squiggly, an easier task, it just had like squiggly 𝐐𝐵𝐴𝑛 and 𝐒𝐵𝐴𝑛 element. Maybe when they write it like this, they actually mean this. So instead of just writing sum, I could write a sum of -1, 0, and 1 in the squiggles. Strange. But this was a simpler task because this meant that we were supposed to, and maybe it was like, you could imagine it was one particle, and the one particle can have these spin states. So for the partition function you really need to like add up the possibilities or the combinations that the particle 1 could have -1 spin or 0 spin or 1 spin. So we would just add all these states together, all these microstates. So that seems very intuitive. But maybe, yeah, maybe it's just the same now. So if you have two particles, this would just jump in. Okay, particle 1 can be -1, 0, 1. And then it would like loop over again and say that particle 2, it can be -1, 0, 1. So you have to combine them. But this is a fixed number. This is always fixed. But when you write this, seems pretty different. Maybe really you can dump this down. You don't need a count for n0 and n1. So really you could just look at n0 and put in that, well, n0 there must be, like if you have two particles or two systems, n0 can be 0, 1 or 2. that would like automatically mean that n1 also contains 0, 1, and 2. So maybe that's why you can just write ni. Because I is not particle index, I is just... Okay, so seems more... It seems less intuitive to have it like this way. But that's the way they chose it, so... Because that would mean that you have had to... Well, it is actually the same as saying Ni is also the same as sigma n. There's just one thing there, sigma or n, could be n. And it could be I. And I think here was n was... but here n was the particle index. Yeah, so this basically means that when you do this sum, you would get but doesn't that mean that ni is element from 0 to n? Oh, so that means it's not the squiggly, haha. But how can ni not be a squiggly? Annoying notation, annoying. Because ni would really be not a squiggly, but what's this called? Square bracket thing. And just that or okay. Instead of writing n is a integer, you can write squiggly. Not up to n, but let's do this again. Because there could be... It depends on how many particles there are. If there's one system or one particle, then there could really be that n... then ni would really be 1, 0 or 1, because there's either 0 ground state particles, or there's 1 statistical, yes. Mr. Steele, Semper Fi. It was the students of 𝐒𝐚𝐬𝐿𝐬, a Norwegian physicist or professor. I don't remember what university he was at that time. But they called his statistical mechanics course Statistical Mechanics, because it was so hard. And my professor told me about it, and I double laughed. Because firstly I laughed because that's funny that 𝐒𝐚𝐬𝐿𝐬 made it so hard for the students, so they called it Statistical Mechanics. And it's also funny because my professor's course is also pretty statistical. So I got a 2 laugh out of it. that means that Ni for one system, Ni would really be just like 0 or 1, but for for two systems, Ni would be 0, 1, or 2. Doesn't that mean I can say that Ni is 0 and then like point n? So in one system that's just 1 and then I can reinterpret Ni. Interpret for each system. You're right. Yes, that was I asked Oracle, the ChatGPT yesterday, and it also wanted to use I on the particle index, and as you see here, I started for like 20 minutes ago. I did that because I thought that was the way, and then it works perfectly fine. But we are trying to use the notation of my professor, and he likes to use I as just the energy level. So we're trying to see if my professor actually used that notation. And that was we found out it was normal. It was a Harvard paper that did that, and I watched a little bit of lecture this morning, and I was so lucky that he actually was lecturing about this. And then he also used the Harvard notation, so I'm just gonna double check that he actually uses that Harvard notation in the problem set as well, in the solution. So we just now figured out the squiggly sum. Because then you would get so I have to switch page. I feel like when I switch page, I erase all my memory. I know nothing of that previous page. That is statistical. So that means when we keep I in 0, 1, and let's say you have two particles and they like to use this. Oh, it's a very ugly squiggly. And I'd like to use this notation. That really means that you would get some terms with n1 by 0. Okay, n0, sorry. That's also new. We get n0. And then how many are there of n0? We can just say that it's n0 here, n1. That means if you have two particles, you would have to test and throw inside the rest of the partition function. You would have to throw in that you have 0 of ground states, then you have 2 of excited states, and then it's a sum, so it will be plus the next system, or the next possible configuration of the systems. You have 2 systems, 2 particles. The next would be that you have 1 of the ground state, and you have 1 of the excited state. 0 ground state. But you could also, maybe I should maybe here. You could have, no, you can't have 0 ground state and 0, 1 excited state. That's not possible. And maybe this is, no. Then you could have 2 in the ground state and 0 in the excited state. Interesting. So, to make it idiot proof and idiot formulated, you could write n0 equals 0 in the first term, and excited equals 2 plus n0 equals 1 and n1 equals 1 plus n0 equals 2 n1 equals 0. Okay, so this is what they're summing over. And inside the sum is E minus beta. So that's one mystery figured out. You're having flashback to the horror. Well, I can confirm your flashbacks. It is horror. Indeed. And then it's like it's soon May, and May is coming like boom. And I have assignments in statistical and assignment in semiconductor physics course, basically to the end of April, start of May, and then it's like just in the end of May the exams come, and statistical mechanics have been so statistical that I'm just at problem set for week 6. Oh shit. Admitting the truth. We are on the highway to hell. But at least showing this sadisticalness forces me to focus more. Share my horror with you. It makes me focus a little bit more, thankfully. But here they say just I. Is there no way to say that make this better? No. Then it's I of Ni. Now we come to the second problem. So let's say for the first term, you would get, this says that you would get minus beta I. Okay, so this is a 2-sum, is I0 and 1. Okay, okay. It says that I would get E of N0 plus E of N1. The horror. It's like that movie, that action movie. Not Platoon. Yeah, yeah? No. That other war movie. Then E of N1. Okay. So what in Earth is E to N0? If we can figure out this term, then okay, so in this case it would be, this term would be minus beta E to N0 is 0, E of 0 plus E of 2. That's weird. Because doesn't this mean if it's E of N1, that means E of number of particles in the excited state? Because there are 2 particles or systems in excited state. But that means that this should really be E. Oh, sorry. Because we know Svensson said that the first particle has 0 ground state. Oops. And the second has 0 in ground state. The first particle has epsilon as excited state energy, and the second has 2 epsilon. The camera has an auto shut-off timer. How convenient. Oh, there it is. Yeah, so particle 1 has 0 in ground state energy. This energy it has epsilon in its excited state energy, and the energy of particle 2 in ground state is 0, and it's 2 epsilon in excited energy level value. But if this is correct, I should get the energies here should really be epsilon plus 2 epsilon. Should be 3 epsilon is the energy level when you have 2 excited ones. But does this give it to me? N1 is 2. So you need, this means that that would be 2 times something. 2 times what? That's supposed to give me 3 or something. If they use the Ni notation, that's what I'm very curious about. Because now, if you refer to where Ni is just your excited state or ground state, it seems, well, I must say I'm not really sure what they use. But since my lecturer, my professor, also used that Ni was number of particles in the ith state, I would think he would do the same. But of course, this is a problem set of Svensson's book. So maybe Svensson is funny individual and does it on his own way. I'm not sure. I asked when I asked Oracle. The Oracle said that it wanted me to use the Ni notation though. So what I'm wondering here is, I think this is the place we can find out if it's the solution up there, if it uses I or an Ni notation. Wait a minute. Yes, that's my professor solving Svensson's task. So I mean, so that means that the notation used up there must be right. But I just wonder what the meaning of the notation is. You Galva Bart, right? Yeah, you just jumped from Twitch to YouTube. I didn't understand right away. So if this could be 3 epsilon, then the I notation is correct. Or the I notation is what the professor used. But this should really be something with N1. Number of particles. And I don't see how you can get e of 2 to become 3 epsilon. 2. Oracle said EI of NI was NI times I times epsilon. Okay. I mean, if you use this notation, it works. It works, I think. But I don't think this is a notation that... I don't think that's the notation that then the solution is using. We can recap. Here it is. Yeah, because Oracle says that Ni is just 0 or 1. But we really want that I is 0 or 1. So, I mean, you could just... but if you switched it, it would be E of I equals I times Ni epsilon. But that maybe doesn't make sense. It doesn't make sense if you say that Ni is the number of... Because I don't see how you can get... And yeah. Sorry, I was using showing from the previous task. But it's just because in the solution for the task we were working on, they jumped immediately from this to just to this. That's a bit far, but they still use like the same notation. So if you just focus on this, and I think this is right too, but this is not correct for the second task. Remember, you then have to have epsilon n, small n, and then product symbol n and small n, as you showed earlier or yesterday. But this is still where we start off in the second task. I'm just trying to check how this can be. When you say that Ni is the number of particles in each state. But I think it might be possible we just have to find E of Ni that gives us that. So how can you have... You should... Maybe they're just saying that E of N1, I don't know, N of... Maybe this is what they're doing. Just not cheating, but like using a different expression or definition of E. So maybe E of N1 is the energy of the excited particles. But then you don't really get an equation. Do you? Because if this was just, or this must be, what we know that must be true is that this is E to, or this is the energy of the first system plus the energy of the second system. I mean, if you just say that this is a definition, then it's okay, but shouldn't it be an expression? The name of the book, it is An Introduction to Statistical Mechanics and Thermodynamics. Great title. Thank you, brother. It is in the style of Goggins himself. And you know what? He's actually watching me right now. Every second. You just look into those two eyes, and it will rip your poopy pants off. And then it's time to get back to work. Because if in this case you have two excited particles, that would mean that you will get E of 2, right? So how can we make an expression that gives us this by multiplying or something with 2? The oracle way was pretty nice, but it doesn't work this way. This you can say that it's epsilon. Maybe you can say it's a sum. Yes, I'm studying at the University of Oslo. And technically, my master program, it's called Master in yes, like 3 names. The one is Quantum Technology, Materials, and Nanophysics. Yeah, that's what it's called. It's pretty broad, so I could choose whatever I want, basically. But we are like focused on condensed matter, solid state physics, basically, material science. And I really want to delve into the quantum realm. So I chose statistical mechanics because I basically had to. I wasn't pretty sure what it was, but I knew he was a good professor. So I think, yeah, okay. If the only choice I got, it's a good one. And luckily for me, it both includes much stuff for condensed matter and quantum. So I was really lucky. Universe did the decision for me, basically. But one way is that we could cheat and say that it's a sum up to n1, maybe? Or because Swenson said that assume that energy of the excited state of the nth subsystem. But Swenson, maybe we can't use. Oh, god damn it. Maybe Oracle was right. And this is just like a task that Swenson just uses his own notation, annoyingly. Because he says, I don't know if you can see this. Yeah, you can see it. Assume that the energy of the excited state of the n subsystem is n epsilon. And that's a small epsilon, but it is n times epsilon. So that's okay that he says that if you are looking at particle 1, its excited state would be 1 times epsilon, and excited state for particle 2 will be 2 times epsilon. But really, if he's saying that it's the n subsystem, the excited state of the nth subsystem, subsystem 1 and 2, that means that, maybe, I think that means that 𝐐𝐮𝐚 actually cannot be using the Harvard notation and the ones that my professor used in the lecture. 𝐐𝐮𝐚 is caving his own way. Excited state 2. Because that means that if this is the n's, then n is really the nth particle. N particle. And if n is the nth particle, I think that means that we cannot say the n is, or we are creating our own symbol. You know, this symbol is like leading to. So we have something there, pa 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 pa, leads to that pa 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 is true. But now we invent our own symbol because I've never seen this before. Maybe it is already invented, but if this is, if n represents the nth particle, then it does not lead to, I think, that ni is equal the number of particles in the I state. Maybe. Yes, it seems like 𝐐𝐮𝐚 is using that n is the nth particle. Then Oracle was right, maybe. We're just gonna try a little bit more to see if there's possible to use this notation anyways. Just in case my professor used that notation when solving this problem for us. And I like to say that for statistical mechanics, you really should have a solution to the solution, because it's so damn difficult. Yes, I tested that n was the nth particle, or we then used I instead, but that's, I think my professor changed it to I instead of n for some reason. Or maybe not. God damn. But at least I tested something and used some type of notation some minutes ago, and it seemed to give me right answer. But must make sure, so I want to use the notation of my professor. Because when the exam comes, that's probably what he's gonna use. And then I'm gonna be calculating something completely different. And the professor is gonna scratch his head while he's correcting my exam. If he's not using the same as me. But really, Swenson actually says this, that it's the nth subsystem. That must mean, in his words, that n is the index of the subsystems or particles. So n1 would be particle 1 and n2 would be particle 2. So what's interesting now is that it seems like the solution switches it so that it's I. Because Swenson never mentioned any I. So I think it's pretty obvious that my professor is introducing I, or this was Mrs. S that did probably these calculations, that she switched. She's like the group teacher. She has group sessions and does and also corrects assignments and probably makes this. I think she made these solutions. So I think Mrs. S introduced I herself. Because I don't think Swenson uses any I's. Yeah, you can just see the Hamiltonian. Swenson's Hamiltonian goes from n equals 1 to n. And yeah, inside the here, this should really be the Hamiltonian. And then you see it's I instead. Whew. So the question is, what is Mrs. S using as I? Is it the Harvard notation, or is it that I is the number of particles? That she says that it's the ith subsystem is I. That must be I epsilon. And according to the Harvard notation, I is 0 to 1. That is not the same. Yes, that means we have confirmed that Mrs. S is not using the Harvard notation. Because... Or then she has at least changed this E. Okay, yeah. Because this is supposed to be... it's weird to change the task so drastically in the solution. So that's probably unlikely. I think Mrs. S means that I is particle. Because this sum in the... Swenson says that this sum is from n equals 1 to n. That's the particles. So it's weird if she would do 2 changes, that she would, or 3 changes really. It's very odd if she would change this I to not, or she would change this to I, that's one change. And if it's 3 changes, that means that this is not, and if she's using the Harvard notation, that means that this would be I, which is the index of ground state or excited states, 2 changes, and then she must change this, or else this doesn't give us the right answer. Unless we can find a clever way to, when you have E of 2, how can E of 2 become 3 epsilon. And if you use the Harvard notation, what? Then there's really no way to... The system is a collection of particles with different energies EI. Oh, that's what's a bit Galva mentioned a bit earlier, that what you said is probably the normal way to do it, but for this problem it's the odd thing that we have a big N number of systems, because a subsystem or well, he says subsystem. Is it fair to say that a subsystem is its own system? Yeah, so maybe you are right. Yeah, you could say, if you change... Yeah, you're right. The system is a collection of particles with different energies EI. And if you have to use the strict, I like to say particles, but if you use the words they use, terminology, that would translate to the system is a collection of subsystems with different energies. Yeah, so you're right. But I will just say particles. Makes much more sense. So you are correct. But really, if you use the Harvard notation, you have no... How do you get this? Maybe it's faculty? Yeah, maybe it's... It can be faculty. No. Then you don't get 3. Still good, don't get 3. Well, if you have a sum up to n1, that would mean that when n1 is 2, you have a sum up to 2. And what if you just say this? Program. That would be 1 epsilon plus 2 epsilon. I think this is the only way you could... If you use the Harvard notation, your E of n1 must be the sum n1 well, it can start at 0. Let's do that again. If you use the Harvard notation, Okay, but that means you have a sum inside the sum. It's really ugly. That means this E of Ni is also a sum. That's peculiar. Is that possible? Well, maybe not. I don't think there's another way. Or, I mean, ENI is just a number, so even though it's a sum, it's still a number. So you can't just keep it in here. But if you... Or let's look at this. But if you switch... Maybe this reveals that it's not possible. Because here she put in minus n beta epsilon. If you have... So now she said this n, what's... and okay, so this n... Now so she's saying that n is particles. It's a decaying exponential. Yeah? Shouldn't it be decaying because it's a minus beta, maybe? I guess. Yeah, it might be. And really now we're looking at the partition function, the z. So that's just like, it's not thinking about how many particles are where. It's just mashing up every possible outcome. You know that it is possible to have 0 in the ground state, and it's possible to have 1,000 particles in the ground state. And the probability will probably be otherwise. And what we're really looking for in the set is just combining all the possible. It's like combinatorics, if I said that correctly. Combinatorics. So it's just like saying that if it's 0 particles in the ground state, that's one possibility. It's like adding up all the possibilities. Page 268. On the way. Normalization function? I'm not sure. I like to think about the partition function as like all, if you think of a coin toss. Yeah, if you integrate it over some of it, that must be one, yes. Why is it not page number here? 268, what the... They just like, they forgot to put in page number? Okay, it says here 297. Yeah. Maybe you looked at the PDF version. Do you know what's the headline? I think since I logged into the university, I got the second edition. Leperi de Cametu, thank you for the follow. Welcome to the Marine Corps. Colonial Marines, hoorah! Factorization of the partition function. Okay. It's probably this. Did it change? I can't. Yeah, there it is. Oh, they added a whole new chapter in addition to. Gray box. Light gray. Was it upwards? Or down? Yeah, my screen has like weird. So maybe it's not gray for me. Something with the screen. 2450, yeah. And oh, you said it has NJ, and then okay, so that will be like NI. This one, the flip. Yeah, I saw that. That was the trickery of. I found it out if I just took each term and then multiplied together. I found that this was true. I just want to see. Here he uses squiggly J, NJ, and then he has J is each particle or system. If you, that depends on. This is really. It was very easy to see when you write it out. That was the only way it was easy to see. But luckily then I had an easier system. The one with the spin -1, 0, and 1. Because it was when you multiplied. So if you just, when you had this, and you write it out, so yeah, you can probably do it like, no, they already switched here. If you start with this, and then you bring, since it's sum here, you bring down this, the product symbol, then it's squiggly, and the product symbol, like we have here, squiggly, product symbol, and then if you just keep it that way and do the multiplication symbols, this turn boom 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 many e's, and you try maybe with 2 particles, then you need to remember that this sums, that means that you have to test every possible value of ni. Then you see you get some terms of boom 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 e's, and then multiplied or then plus boom 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 many e's, and then it ended up being that you could see that it was some terms here plus some terms here. I think there was something you could see that you like, if you also write out what this means, then you see that, oh, this is equal to this. So take the product sum down and write it out for 2 particles, and then take this and just write it out. This is just, you have to put in the values of ni, and then you would see that this written out was equal to this written out. Yeah, because when you have squiggly, it means something else. When it's not squiggly, it's just that you have to insert the possible values of ni one time. That's why you just get that's why you just get 1 plus this. Because you see they put in that ni was 0, no, or n of 0, and then put an n of 1. Maybe this is the key to understand what. Because if you look at what notation they used here, then we can understand what ni means. So you have I, and now I is... Yeah, maybe this confirms that Mrs. S is not using... Maybe this confirms that Mrs. S is not using that I is... Here you see that I cannot be an element of 1, 0. Right? Because I is 1 on many terms up to n. Yeah, so maybe this confirms. So she isn't, or she or Swenson is not using the Harvard notation that I is 0 or 1. Yeah, that would be with the Harvard notation. But now, but I think actually, but now n I is just 0 or 1. And I think the proof of why that is so lies right here. This is, be in mind, this is when all the particles have the same excited state. But that doesn't really matter for what the squiggly ni means. Yeah, unfortunately it's, I think, yeah, tomorrow would normally be like a group session where she helps out with the problems. But lucky for me, it's Easter. Oh. Just when I was really getting into the tasks with the problems. But you see, I think now we can prove actually that she's using ni as just 0 and 1. Because she has, let's do this really clear. She has this and I. So that, firstly, that means that we see that I goes up to n, and n is clearly the number of systems or subsystems we have. And then she says it's ni here, e to minus beta e of ni. And then she says that this becomes equal. She doesn't change the product sum, or you don't need to change it yet. But she puts in, it seems to me then, she puts in e to minus beta e of 0 to the minus beta e of 1, right? And this is the task where you have all the same. Where you have all the same excited states. That's why you can just throw this n to the this sum up here as power to the n. No, this is nothing. Now we don't need to think about if n is equal to 2 or not. This is actually for all n possible n's, where n is the number of particles or subsystems. So now it seems like she put in Ni. You see, she fulfilled the sum, you know. She just put in E of 0, that Ni was 0, and Ni was 1. So she seems like Svensson and she is using completely different notation than the Harvard one, and my lecturer, the professor, in his notes. And I can just try something, and this is also what Oracle says, because that would mean that E of Ni was Ni times I epsilon. I is the particle index. So let's just ask Oracle. So maybe Oracle was right all along. This goes to this. We assume each of the n subsystems has 2 possible energies, E equals 0, E equals E. Hence Ni is 1 and 0. Indicates which state subsystem I is in. Okay. Ni equals 0, 0. And this is, again, in the task 1, it's a bit simpler, where every particle just have 0 or epsilon energy. But it's just to like understand Mrs. S notation. Yes, and I equals 0 to 1. 2-level subsystem. Evaluate the inner sum for a single subsystem, yeah. Then it's just putting in Ni equals 0 and Ni equals 1. That's 1 and that. That means that this sum is just... That is, this sum is just these two terms. And then that's 1 plus E there. And then you have like the product symbol outside. And when you have the product, and each term or each product is the same, then it's just to the power n. So finally we have debunked that, unfortunately, 𝐐� needs us to use a different notation. So we can't use the... Unfortunately, we can't use that Ni is 1 or 0. We can do it. But it's not what they're doing here. It would work if you just say... Then you have to say that E of Ni is a sum. Another sum. Then E of Ni must be the sum of N epsilon. So... Whew. Let's see... Then we can go back to this. This was for the old task. So for 2, 1. For 2, 1, we would get this. And I... A little bit annoying that they don't use the standard notation, but hopefully everyone understand. That really means that you have to really read the problem task, because it's really explained here that when 𝐐� says assume that the energy of the excited state of the nth subsystem, so that means that n can't be, or he's using n but Mrs. S is using I. But at least that means neither 𝐐� or Mrs. S is using the Harvard notation, and the notation my professor used in the lecture I just watched in this morning. That's even more confusing. But we must move on. The ground state is the same for all particles, all subsystems, so it's always 0. E to the 0 is 1. But this one is different for each particle. Ni or N1 N1 times I times epsilon, because I is the particle index, or they're using it as in such way. Yeah, so that's... I don't know why... Mrs. S, Mrs. S. Why do you use... Okay, maybe... Okay, she switches back to small n because it probably would be... Yeah, it would be wrong if she had used small n back here, because then you will have, if this was small n, like in 𝐐𝐮𝐻, so 𝐐𝐮𝐻 probably would also have to do the change to I, but because you get two indexes or variables. Okay, this is particle and this is the I of each particle. Well, that's weird if... Oh no. Oh no. If I is the particle and we say Ni. So this is not N1, but it is Ni. But it's just that because Ni is really now... Yeah, Ni is the 0 or 1. But since I is particle, that means that n particle 1 can be 0 or 1. Yeah, so it's really like this. N1 is 0 or 1, and N2 can be 0 or 1, or particle 2, particle 3 can be 0 and 1, etc. But it can only be one thing at a time, you know. So this is... Yeah, when you have this sum, it strips down, it doesn't care what particle I it is. It is just that we have Ni is 0 and Ni is 1, because that's all the possibilities we have for any ni, because n1 can be 0, n2 can be 0, n3 can be 0, or n1 can be 1, n2 can be 1, n3 can be 0, etc. But all this sum without squigglies means that it is supposed to just put in the possible values of ni, no matter what ni we are looking at. No matter if we are looking for the n of particle 1, 2, 3, or 4, 5, 6, 7, 8, 9, because all those can just be 1 or 0. So then we put in that it's for the particle. That's why we still have the product symbol. It makes sure that we are multiplying all of these together. That means, say, if you have two particles, there will be two parentheses, and each parenthesis would have the ground state, excited state, and then the next would have the ground state and excited state. But we know that ni, when ni, the ground state ni is always 0 for any I particle. So any n1, 2, n3, n4, n5, and n6, etc. They're all 0 in the ground state, but they're all 1 in the excited state. So really here, ni for any I particle is 1 anyways. And any particles ni is 0 in the ground state. So that means we can exchange ni for 0 here and ni for 1 here. Yeah. And then it's nice to use this. That's what Mrs. S is using as well. But then you get this. And really you can just keep it as I. But then you can relabel it at, instead of using that I is the ith particle, you can switch it to minus beta 1 times n times epsilon. Because it wouldn't make no sense to have n to the n here. You can't, if you have a small n here, n particle to that, you can't have n of n. Or that seems weird, at least. Oh, finally. Understand what they did. In their way. Yeah. And then we had that wasn't it like this? My head is cooking. You remember the cooking? Yeah, I think seems pretty hard. Now I remember I was really sloppy and lazy the first semester of my bachelor. I think I would occasionally, maybe like 5 hours ish working, maybe 6 a day when I had no lectures, and doing some programming and stuff. But then I would like get home, I think about 5, like 5 or 6, get some dinner that was like just bought this bag and heated it up. And then played Escape from Charcoal for like 5 hours. That was my day. Yeah, and I remember had this crazy ritual that I used to watch a movie in the morning. I woke up 7, and then watched a movie and breakfast and some hot chocolate. Yeah. You're from another period in space-time. Actually, I had the same professor in this. He had the quantum mechanics course for like 1.5 years ago, and it was really great, and I could actually understand some things, and I worked very much with it. It was like quantum physics course part 2 in the University of Oslo. So last semester I thought, okay, we need some more quantum. That was cool. So I tried basically, I think you could call it like UIO, University of Oslo's third quantum mechanics course, and it was called Modern Quantum Mechanics for some reason, and the professor didn't know why it was called Modern Quantum Mechanics. The faculty just decided for that name, I guess, many years ago. And I think I got, after the bachelor was finished, and last semester, all motivation disappeared, and the working was even more hell than ever before. So modern quantum mechanics went straight to hell. And I think basically maybe it was even harder than this statistical mechanics. At least we didn't have that. We didn't have the blue wizard professor, unfortunately. So to not mess up my master, because I also have to write master thesis, technically 10 study points this semester, because I just have 2 courses, and then I have 1 course next semester, and the next after that, last semester, then it's not allowed to have any courses. And yes, it's safe to say I failed the modern quantum mechanics, so I have to take it new exam to the fall, and that means I must pass it then, because it's not allowed to take any courses the semester after. So the plan is to, and luckily this is like a big warm-up, or almost the same as the modern quantum mechanics course, in the way it's you have to calculate things and integrals and sums, and there's many similar things. So the plan is to man up and study quantum mechanics, modern quantum mechanics, the whole summer. If I use all the summer, then I should be pretty good at that when the next semester starts. So then I don't have to do very much modern quantum mechanics that semester, and focus much on writing the master thesis and the one other course I have. Because if I do no modern quantum mechanics in the summer, that basically means I have 2 courses the next semester, because then I have to work basically every day with quantum mechanics and that other course, and then there will be little time to write master thesis. And also I like to take one thing at a time. Whoa, you did it on your own. That's cool. You should really watch, there's a lot of Feynman lectures out there. Some of them are, and he's very good at explaining. He tries to, because it seems like actually when humans understand, it's like maybe we don't understand, because that's a weird word, but we grasp things when we can think about it and imagine it in our mind like something we are used to. Like atoms are billiard balls, or or things like that. So he explains. He often makes such examples that you can relate to real life. We also actually have one in our class that I think also is retired. I'm not sure why he takes statistical mechanics, but he's there every lecture. So what can we do now? Does Mrs. S get the same as me? I need to check if there is something more I can do before. This is just a sum. Particle, 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 particle. 1 plus 2 e's plus 3 e's. I don't think you can short that anymore. Let's see what she does. Oh shit. I made a big oopsie. Hey. I differentiated and logarithm of this. No, I just omitted the logarithm. Oops. Big oopsie. The logarithm of this is really 1 over 1 plus e minus beta. Then the core differentiated, and that's this. The core differentiated, that's just minus n epsilon. Can we do anything about this? And I forgot another thing. No, I didn't. Or did I? ln 1 differentiative of ln of u is just 1 over u. And then times it's the core differentiated. I kinda dread how I'm gonna learn physics after university. Because if it's this hard to learn physics, you have to like do endless amount of tasks. How am I gonna do it on my own? I see some books actually have problems, but I'm not sure if they have solution. How am I gonna get that? Just pray that Oracle ChatGPT it's so powerful that it can solve any physics tasks in any book. Now it's not that great to solve tasks, but it's very great to understand what's been done and analyze what's been done. Maybe you can... Yes. Yeah, she just multiplies with e to the beta n epsilon up and down. We can also do that. If you multiply with e to the beta n epsilon in the numerator and denominator, that's just the same as writing 1. So that's allowed. We can do it. Then we get this. And this 1 becomes e to the minus, e to the plus beta n epsilon. then plus 1. Yeah, that's the final answer. Quadra e multitus demonstrante, or something. Yeah, learning the concepts, yeah. It's probably, if you learn the concepts, and then maybe, like, if you need it for work or something, then it's probably much easier to try to understand the calculations after you understand the concepts. So that's good.
After checking several reliable sources, I've confirmed that QED stands for Quod erat demonstrandum,
Well, that's
which is a
interesting,
Latin
Oracle.
phrase meaning that which was to be demonstrated. This phrase is traditionally placed at the end of a mathematical or logical proof to signify that the demonstration is complete. Quod erat demonstrandum, wikipedia.org//quod erat demonstrandum.
I think it's more fun.
The term has been used for centuries in academic writings and is a standard way to conclude a proof, indicating that the original statement has been fully demonstrated by the argument.
Yeah, thank you, Oracle. Thanks for the response. It's really explanatory. That's the word. Yeah, thank you.
You're welcome. If you have any more questions or need further assistance, feel free to ask.
Yeah, I will. Suppose we are in the low temperature regime, for which kBt much less than E max. Why does that matter? Calculate the average energy. Oh, we have to do it again. Or no, we have to, because this is the average energy. And I think and you can also say the average energy, total, I think, that's also equal to or this I here, to this. Because you just sum up each energy value of each particle. That would give you the total energy of this system. So now, Mr. Swenson is asking, demanding that we calculate the average energy. Well, roger that, Swenson. Oh, you're going into quantum electrodynamics. Wasn't that Feynman? Feynman was very involved in that. I think maybe after, if you go even deeper than quantum electrodynamics, I think Feynman said that quantum electrodynamics was combining Maxwell laws and quantum mechanics. Something about that. And yeah. And I don't know, is it just entirely different? But maybe what came after quantum electrodynamics was a quantum field theory? Yes, yeah. I hope that I couldn't take quantum field theory. I don't know, maybe I could. So maybe I should have taken quantum field theory course instead of modern quantum mechanics. Yeah. And it was quantum electrodynamics that then they figured out how to calculate it properly after those 20 years. Maybe you can come to Norway, take some courses. I think anyone can just take courses there. Well, if you want problem sets, you can set. Just surprisingly, you can go to this page and you can see. From the Netherlands. Have you heard the Norwegian king making a possible dry joke about when there were some, I don't know if it was the Norwegian team versus the Netherlands. Is it Holland? It's also called Holland. Well, there was also a football player in the Norwegian team called, yeah, it's basically pronounced exactly the same as Holland. So yeah, so they the players from the Netherlands team was wondering, why are the Norwegians screaming Holland, Holland? But it was actually the name of the Norwegian guy. Yeah, so this yeah, it's written Holland. Yeah. This looks pretty similar to what I'm doing. Many integrals. Like always integrals. But what's different is probably these, when it's field theory stuff, then you get these, no, this is just derivative, yeah. But you get D4. Maybe it's not. Okay, this is a bit different. This is, yeah, some Lorentz scalars. Yeah, even more integrals. You can just forget sums. And this is like, I don't remember what it's called. It is like 4 vectors, I think. Yeah. Because they are taking time as its own axis. I think maybe some of the reason I didn't take this was because it was relativistic. That's a bad excuse. This is very like classical mechanics. The 4th dimension, yes. Now we're talking. Yeah, this square. I don't remember what that was. More integrals. Yeah, this is like quantum mechanics. You have P. Not sure what P is, but this is some sort of operator, I think. Should be. Klein-Gordon field, huh? You know what? If I got some spare time, or when I'm retired, I might try to do this. So let's save it when we can. Ah, just momentum. Ugh. Yeah, and this is some serious quantum field theory. It's angry. This is aggressive. Aggressive quantum field theory. Oh, where did they go? I'm saving this juiciness. I can't let this slide. And then, like, in some months when they're starting the course again, they like delete these because they're, oh, it's not gonna show the solution. But if these professors understood normal people, laymen's, they would understand that you need actually a solution to the solution. It's so difficult. So it's not fixed. So it's not that quantum mechanics is obsolete. It's just that it's refined to certain calculations. This is exam. Feynman vertex rule. Oh snap. You heard of that one? I've never seen this big M before. It's not big M, it's a weird big M. Yeah, another application area. Do you know what you use quantum field theory to today? Is it applied in some... Okay, it is condensed matter physics. Do you know what areas in... Is it like calculating phonons or electric properties maybe of the crystals? Is it like used in semiconductors? Yeah, particle physics. Oh, okay, you meant, yeah, quantum mechanics is condensed matter. And, oh, okay. Quantum field theory is particle physics. So maybe I was very lucky because I'm going condensed matter physics. So maybe I was lucky the universe was guiding me without me doing the proper research. I didn't try to not do the research, but maybe not good enough. But then I was lucky that I chose modern quantum mechanics. Because there maybe it's because, as you mentioned, that you have a certain set of n atoms or n subsystems. What is Emacs? Hmm. Yeah. Good books is important. Well, thank you very much for the chat. And good luck to you too with continuing with the quantum field theories. Or quantum electrodynamics first. Roger that, Galva.
Hi everyone, welcome to the first mini lesson in the online component of Physics 413. We're going to talk about how to extend our ideas about the canonical partition function tool to composite systems where the all energy to canonical partition function.
Yeah, exactly what we're doing.
We derive an expression for the average energy of a single particle in a subsystem of the canonical ensemble, only in terms of this derivative of the single particle partition function. We also noted, even way back then, this was before spring break, even
Yeah, that's useful.
Alright, welcome to mini lesson 19.
Maybe that's
the theory of Bose-Einstein.
the first and second video.
The online component of Physics 413. We're going to talk about how to extend our ideas about the canonical partition function tool to composite systems where the components are distinguishable. That's an important concept. So let's review canonical partition function for a two-level subsystem in equilibrium with a reservoir at temperature T. So we remember reservoir single minus one that doesn't restrict us very much. The Boltzmann factor associated to each of our possible energy level diagrams. So
Hey,
the
that's
first one
exactly
we've got
what
e
I
to the
did.
minus beta
0,
0,
0, 0
ground
epsilon.
state. The second one we get e to the minus
I think
beta
0
epsilon,
again.
which is just
Okay,
coming
yes.
from the
You can flip
epsilon
them.
energy
And then epsilon, epsilon.
of the red particle in the excited state. And we get the exact same Boltzmann factor when the purple and the red are switched, but that's not redundant in this circumstance, right? Even though these Boltzmann factors for these two diagrams are the same, they still need to be added together in the distinguishable composite partition function. That's important to think about. And then finally, when we put them both up here, we get a total energy of 2 epsilon, and so we get a Boltzmann factor e to the minus 2 beta epsilon. So we add all that up, we get Z2, where the 2 says we've got a composite system with two particles, the subscript here. We get 1 plus 2 e to the minus beta epsilon plus e to the minus 2 beta epsilon. And if you stare at that for long enough, you'll probably start to see that that is exactly 1 plus e to the minus beta epsilon, quantity squared. So in other words, you take the Z1 that we already knew about from our last lectures and just raise it to the power of the number. Important that this is Section 6, we said we've got particle fundamental. Let's go. This one, or this one. And then for every possible choice of where to put the first part of the function when we have distinguishable mechanics. So by contrast, distinguishable statistical mechanics is going to come about when the components of the system that you're thinking about are more like organizational concepts rather than fundamental building blocks. And so an example of this is the oscillators in an Einstein solid. So these are not actually particles, right? The oscillators in Einstein solid are not the atoms. In some sense, they are the vibrational degrees of freedom associated with the atoms. And so there's no, the way nature works is that thinking about those degrees of freedom is not they're not indistinguishable components. They are actually distinguishable.
Thank you, Galva.
Conceptually, it's allowed.
See you
And
later,
so, yeah,
buddy.
The second way to say this, and
You'll-
this, again, is actually just
you'll
another
be
example
back.
of the oscillators in the Einstein solid, is that anytime you're dealing with different degrees of freedom, these are just organizational principles. They're not they're like breakdowns of different modes rather than actual particle constituents. And so the example is, what if you wrote the total energy of a molecule as its translational energy, its rotational energy, and its vibrational energy, right? If you would put these things inside the expression for the canonical partition function, you would do the same analysis that we did in the last mini lesson, and you would come out with the total partition function, including all of these degrees of freedom, would be the product of the partition function for the translations, times the partition function for the rotations, times the partition function for the vibrations. So again, when the constituents are real particles of matter, they will always be indistinguishable. If they're just organizing principles, in other words, degrees of freedom, you can treat them as distinguishable. And so we'll be doing some examples of both of these in the next two mini lectures. So we'll see you next time.
How is this allowed? Ah, because the first term, you take n equals 0, it's just 0. You can plus 0 anywhere and anytime you want. And we need Rotman. would take us a long time crafting it. It's annoying. It means less time to study. Damn it. Oracle is thinking hard. But 10 people. 10 people simultaneously watching this. God damn. I think it's task 26-3, not 24. Most the harmonic crystal with alternating spring constants. most crystals contain more than one kind of atom. This leads to both quantitative and qualitative differences in the vibration spectrum from the results derived in class. These differences occur whenever the periodicity is altered, whether by changing the masses of the atoms or changing the spring constants. As an example of the kinds of differences that can arise when the periodicity changes, consider the problem of a one-dimensional lattice with alternating spring constants K1 and K2. For simplicity, you can assume that all the masses are equal to m. Well, thank you for that. If the distance between atoms is a, the periodicity is 2a. What is the size of the Brillouin zone? 2a. No. Alternating spring constants. Does that mean that they're like every other? Always 2 pi, 2 pi, 2 pi. I thought it was just pi. What was the question again? The distance between atoms is A, the predecessor to A. What is the size of the brick also? Pi over A. My first guess was correct. Yep. Calculate the vibration spectrum of the lattice. You might find it more convenient to write down equations of motion for the two sublattices. Holy shit. Vibration spectrum. Now we're talking. Now, what in the name of the universe is what in the name of the universe is vibration spectrum? I'm just gonna do an audio check. Oh shit. Oh shit. Oh shit. Let's see if you can get the equations of motion correct. Get a Black Hawk down, Black Hawk down. Mayday, mayday. Welcome, Veer's Owl. We are calculating the universe. You're maybe not used to me calculating physics, but mostly with a war face. From Sergeant Blaine. Well, I'm trying to get the equations of motion of these infinite chain of atoms, which have different spring constants between them. So this is like a simplified version of a material. A 3D material would have atoms in all directions. But let's start calculating on the simplest version, 1D. So the equation of motion, that's very self-explanatory. It is the equations of the motion of one of the particles, and we will consider the first particle. Well, it's not so simple. I don't really understand it myself. But what is understanding, anyways? Well, we are gonna calculate the equations that would govern the motion of this particle and this particle. And that's all we need, because there's just infinite many of these particles. I have forgotten What was the standard formula for equation of motion? So, I'm not quite sure where I'm gonna put it yet, but I think you have to consider the kinetical energy and the kinetic energy and the potential energy. Yeah. Galilean reference. I think that's true. This is like classical mechanics. Complex number S? You can talk as much as you want, brother. The chat is yours. No words of a marine should be taken for granted. You've been here before, right? When we were streaming Resident Evil, I think? Holy shit, this is complicated. It's a year ago since I had the equations of motions. This will be interesting. I don't see the S you were talking about. Or you were just saying complex numbers. Yeah. We will get to that soon, I hope. First, we need to analyze these equations of motion. How they get them. We shall not surrender under any circumstances. Surrender is not an option. So you gotta think about displacements. For this. And that's just forces. So equation motion for particle 1. And if it's 0, let's say positive direction is to the right. So this particle really feels, if this particle is pulled here, it would feel a force this way, which will be equal the displacement what should we label that? Oops. So this, yeah, that means we can just say that it's the position. So it's the place positive here. Positive. This is negative position. Fierce owl. Did you get an answer? Or did you find did you calculate an answer for the equation of motion, or find an expression, in better words? This force will be negative because it's pointing to the left. Okay, 1. If the particle is here, it is pushed to the right by this spring. That's a positive force. So that's, what we call that? K1 F K2. It should be, and it should be positive, but here's the dilemma. Yeah, it should really be still negative outside, because the position will take care of the sign. Minus the position, because the position would be negative. Minus x0 K2, brother. So that would mean that the sum of forces is F K1 plus 2 Let's test. X0 is 0. It's ugly too. It's a little prettier. If it's here, then X is 1, for instance. Then K, the force of K1 no, maybe that doesn't work. Now the forces are basically equal, but they should be pointing in different directions. If center is here and the ball has moved here to 1 meter, this is compromised, but this one stretched. This force F2 should really be F2 should also push to the left. Let's focus on F1 first. This I know is correct. If the ball is here and the ball is over here, then this one is really compromised, and F1 really wants to, this becomes 0 times a positive 1 meter, that becomes minus 1 meter K1 only is minus 1 Newton to the left. Yes. This way. And if you look at F2, when the ball is there, the spring will be like stretched, so it will also push this way. F2 of 1 meter should really be pushing this way. So that means that F2 also needs to be negative. F2 should then be x0 is 0. Okay, 2. Yeah, so it really just has to be the same. So if it's then x is 1 meter and it's minus 1, that is also minus 1 Newton. That is correct. But yeah, so when it's minus, that's weird. Well, we should not think about too much over that. It is giving us the correct answer. I mean, like the math about the symmetry. The physics makes sense, so then we should move on. Then this really is the equation of motion. So it should be minus x k1 minus x k2 but that is only if we say this is atom 1, so that is only if 2 and 3 is still. If 2 and 3 are moving, let's say 3 was here. And what if 2 was here? If 2 was there, if 2 was more negative 2, means that this would be pulled to the left. That means they would pull on 1. And if this was to the right, it would pull on to the right. n yn minus 1. That's okay way to do it. This is yn. Let's imagine xn is at rest. If xn in x equal to 0, then we have yn here that you could say is a position. If it is stretched, positive direction, still to the right. That would mean that the force from y1 upon x1 would be a positive force. Yn on xn, if it's there. So that would mean still be k1. But maybe you could rather think in a term of the distance between them, because the distance between them has to be set is at rest for some specific value. But that would basically mean you could just shift the equilibrium point for y1 to be at y1. this position is x plus y1, yn, question mark. The equilibrium of this is really x0 plus y. Oh, it's been a long time since this. Xn minus yn. What the hell? How the hell does that make any sense? If xn is shifted 1 meter to the right, shouldn't it be plus? So many seagulls outside. Last night I was dreaming or imagining before I went to sleep. I was imagining that I was hearing seagulls outside, screaming like crazy. And it was like 12 o'clock. I thought, oh, seagulls now? What the pan? How can it be minus? Aha! They just pull the minus out. Because you would get minus x k1 and minus y k1 xn plus no, then wait a minute. Yeah, if you have positive x Well, at least this would give you, if this one is shifted 1 Newton. And let's say the spring constant is 1. This is to the right. It would be plus 1 Newton. But wouldn't yn have to be 0 a lot of times? They say minus k2. Okay, okay. But yeah, now that means that they have a plus. They said that when you're shifting xn, you get minus xn k1, the force. That is a force to the left. And then you get, if you offset yn in a positive direction, you get plus yn k1. Yeah, that's right. But what do you say that yn is when yn is at its equilibrium point, and xn is as well? Because it should be a distance. This should be like a Do you know Fierce Owl? Should the could yn be then 0? Does it have its own equilibrium point? Or is it all just one position axis with only one equilibrium point? Nah, that doesn't make sense. Maybe we should talk in regards of equilibrium distances. Because there should be a distance here that gives 0 Newton. If xn is something and yn is something, it should give 0. when these two are in equilibrium. Or you could just say that xn has its own equilibrium and yn has its own equilibrium. That means that xn has its own number line. Like, that would mean that the x, you know, has its own number line. It goes from here to out here at different points, and it's 0 here and like 1 there, minus 1 there, and plus 1 here. But does that mean that yn has its own of 0 here and I don't know, minus 1 here and plus 1 here? Because otherwise xn plus otherwise this doesn't make sense, because if it's on a, if everything is regards to xn's number line, then 0 is here, then we said that 1 was here, that means that 2 would be here. And that would really mean that yn is always 2. So yeah, that really means that yn has its own like calibrating or number line or position line, position axis maybe. Physics is really like back exercise. You can really feel it in the back. Some neck as well. And then you can say that, yeah, because if you imagine when, as I said, xn is in 0 here, and if you have this yn is plus 1. That would really give you a force that is acting to the right, yes, for on x1. To the right, xn from yn. So that makes sense that it's positive. And since they both have the same k1 constant, you can say that the sum of forces on that for this spring is really minus xn minus yn k1. And then it would be the same for just a minus x. Yeah, which maybe shouldn't it just be the same minus? Isn't it a different atom? Yeah, just n minus 1 k2. Yeah, buddy. Isn't this correct? I just took different K1. K2, K1, xn minus y n minus 1. Yep. Yep, yep. Yep, 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 yep. Yes, yes, yes. That leaves us with the equation of motion. For xn, just, yeah. The sum of forces, m x n, the acceleration times the mass is the force, total force. And that is then minus K1 x n minus y n, because the positioning, when you have if you set when you set position, no, the only reason this works is just because you set because you set the positive direction to the right. Yeah. Then minus 2 x and minus y and yeah, buddy. Are you satisfied, Mrs. S? Mrs. S, she agrees. So, equation of motions for yn would be can't be that hard. Well, you would get from the right side you would just from the right side you would just take y1 yn and this would be that, so it should be plus x and plus 1. Did you K2 here? K1, I get K1, 2, and 3. Okay. Am I talking to myself now? Or is there someone out there in the audience using this as ambience, or we're trying to follow along? Maybe it's too, like, not too difficult, but maybe it's too weird to follow along because you haven't seen all of the rest of the things I've calculated. At least the task is up here. We're just trying to find the equation emotions. So for K, for this there will be K2. Oh yeah, of course, it's not K3, you moron. It's just K1 again. Oh my universe. My universe. 2 is always the blue. So 1. For this one it would be 1 to the right side and 2 to the left side. Is it then just x1, right? Yes. We are victorious. The day goes incredibly fast. Scary. So what's next? Strategy A, B, C, D. for this to be true for all m, k, k2, k1, k2, each term in the sum of x must be 0. This is on the form 0 equals mk m and x. You need a matrix.
People need dramatic examples to shake them out of apathy, and I can't do that as Bruce Wayne. As a man, from flesh and blood, I can be ignored, I can be destroyed, but as a symbol, I can be incorruptible. I can be everlasting. What symbol? Something elemental, something terrifying.
Okay, so she doesn't mean that strategy, like you have different options. She means that the strategy is A and then B. Okay. Equation 26.5. Jean-Baptiste Joseph Fourier. I think he's also French. Here's Owl. xk equals n. What is this tilde? Key to the reason the decision variables define the normal modes. No. Huh. So we need to recap Fourier transformations. Simplify. Xn is that. From Fourier transform we get then x. Okay, so you can take this and double differentiate it with respects to what? X time? No. Yes, it is dot dot. That's time. Yeah. Then you get this, and then you can insert that into the equation of motion. So when you have inserted, you can rearrange so that 0 equals that, 0 equals that, and for this to be time for all, for this to be true for all m, k1, k2, each term in this sum or matrix must be 0. Or each term in the sum, yeah. Sum k. What the flying is that? What is this symbol? It's a really flying thing. Welcome, civilized play. It's going relatively medium, I would say. Or maybe good. Yeah. Trying to refresh some Fourier transform knowledge. We just found the equation of motion. Over here. And suddenly the next step is B. And that is to Fourier transform. Do you mean today's end goal? Well, in general, it would be to learn and expand the knowledge of quantum physics and mechanics. And also some, they might go hand in hand, but condensed matter physics. Perhaps we could, perhaps I will be able to do something about it in my master thesis, and maybe include some include a biological system, because we already know that quantum mechanics finds its way in the biological realm as well. But first, better understand some of the quantum mechanics first. And there's a lot of math. I think one segue I can use is to go via superconductivity, maybe. We haven't come so far yet, and it's a hopeful idea. But it is the goal. And if it gets too difficult, then we will probably look into something similar, or as much as we can. But you could imagine, yeah, as I said, one segue could be the superconductivity. I haven't learned too much yet about the quantum mechanics in superconductivity theories, but I know there is some quantum mechanics in the BCS theory, because the Cooper pairs in superconducting material that superconducts in the BCS way, those Cooper pairs behave like bosons. So then you can get their wave function and etc. But maybe another segue is through materials, because after all, biology is also materials consisting of atoms. But there will be difficulties getting, I wouldn't say pure, but maybe simple enough materials to study with condensed matter. Or maybe we will only maybe reach organic materials, which are probably very similar to biological materials. Yeah, that might be periodic nature of membranes, yeah. That's a good thought. What's really interesting is microtubules. And an old professor, he claimed with some experiments that he claimed that the microtubules, for instance in pig brain, that they actually were superconducting, or superconductor-like at least, because he measured the Meissner effect on a thread or multiple microtubules in his sample. So that would indicate that microtubules are superconducting. That means they send electrons without, or closely without, resistance. And when that happens, you get the Meissner effect. So that means what was it again? Yeah, he pushed a magnet closer and closer to the sample of microtubules, and then he measured that the microtubules set up its own magnetic field to try to cancel out the magnetic field from his. I think it's the transport of electrons. Really like a conductor or a wire. But the wire in a normal sense will have resistance. But he claimed with his experience that there was so low resistance in the microtubules that they were almost superconductor-like. So that means that maybe inside the brain, where these microtubules form, for instance, I think they're in the nerve cells or some axons or something. So that would mean that the electrons could freely move without resistance when, for instance, transporting what we call information. That's just that they're moving in there. it's pretty cool, indeed. And that's why I'm trying to like get to study that. So I've been looking for microtubules in plant cells, because I think it would be, for one thing, that professor is retired. He's giving away all his stuff, I think. So, and also we'll probably get some ethical dilemmas with smashing around some pig's brain. But then I found out that luckily the microtubules in plant cells might be exactly the same as in human cells. Just maybe it might be that they just do different things. But if they're probably very close to equal, and that's good enough for me as of now. So maybe there's a way, and I think I found it, and some reports to isolate the microtubules from plant cells. Then maybe we could reduce them to a 1D chain, maybe. And then it might be possible to do condensed matter experiments on them. That would be really cool. Are you studying yourself? Or is it just free time physics? That's no worries. That's what the chat is for. At which point will you try to develop condensed matter? To explain the biology. It will be like if I can have simple enough maybe if I could have like single microtubules in a 1D chain, that is that they there's like one microtubule, there's one microtubule here and one here and one here, then maybe it's possible to use condensed matter physics tools and experiments and apparatus on them. So I have figured out, seems like there's, and another thing, if I have the tools to do it, even though if it's possible and someone else has done it, maybe it's like, maybe they used some acid or something to like isolate them, and maybe I can't get a hold of that acid. That's another story. But if they're isolated like this, the microtubules really looks like they are like tubes. They're going like in these spirals. So if they were like spiraling over here, this is viewed from the top, maybe we could take, I think it's called ARPUS maybe, or some other, I don't think a cyclotron, but maybe ARPES is, then you could view the band structure maybe of these microtubules, or at least you could try to measure this the electrical conductivity to check if it's true that they are superconductor-like. Quantum phases of matter. That is noted. Yes, you might be able to maybe to like compare with graphene tubules. And maybe it's already been done before and looked at the electrical conductivity and band structure of graphene tubules. So that would be very good to. Maybe it would be best to like do as many experiments as possible. I hope to. If I can do that and then compare, then it's probably easier to see if something is wrong with our measurement of the microtubules. Yeah. It's annoying when you have to buy books. Knowledge should be free. Thank you for the follow. And welcome to the Colonial Marine Corps. Normally, we are like streaming Escape from Tarkov or Battlefield or some first-person shooter. But then I thought, like 4 days ago, I'm streaming and making so little content because I have to do physics. And then I thought, why the heck not? Let's just stream physics. At least I will feel, if there's nobody there, at least I will feel that I'm working on the channel and doing physics. And actually yesterday we had Mr. Galva. He joined the chat and he actually helped me understand. He showed me this interactive board and he could draw and I could draw. It was really cool. So he actually helped me and he found some papers and he researched the partition function we were working on. So streaming actually helped. What is this? Did it come like this army drum music when your name popped up on the screen? Seven hours. Yeah, but this pace, I should really have 17. I'm gonna get through something. Completely misunderstood. It wasn't Taylor. This was Taylor series. It wasn't. That's not. That's not the same as 4-year series. Gotta be kidding me. So how should we do this Fourier series stuff? When I saw these cosines and sines, I started to maybe recognize something. Well, that was it for today, ladies and gentlemen. It's dinner time and editing Sergeant Blaine videos time. Thank you for following us, and you are welcome back tomorrow. Goggins says it best. You are really never He's goddamn right. Thank you for the follows, and I'll be